Hi everyone, this is Christine. I am one of the new Tau Beta Pi initiates at the time of this recording, and today I will be covering some material from BME5020, Computer and Mathematical Applications in Biomedical Engineering. At the time I took this course, I took it with Dr. Ko, but I'm also aware that Dr. Kavdia also teaches this course. I'm not sure how Dr. Kavdia's teaching style is or what his homework problems are like, but hopefully the things that I go over today should be helpful regardless of who you take the course with. BME5020 is also a graduate level course, but I am also aware that undergraduates may choose to take this class in their junior or senior year. So today we will be talking about Euler's method in order to solve an equation or find the solution to an equation. This is an approximation method, so it's not going to be exact, but it should hopefully get us close to the analytical solution or the quote-unquote true answer to an equation. Typically, we use approximation methods for equations that may not cleanly yield a solution, or there just isn't a solution that you can obtain analytically from an equation. So that's what approximation methods are used for. Approximation methods like Euler's method are also iterative, which means that they are repeated multiple times in order to find a particular solution. And you know when you have found a solution when you start to get the same numbers from each new iteration you do. The accuracy of these approximation methods like Euler's method, they improve with smaller step sizes, so they improve with smaller increments that you take when you try to find a solution to each iteration. So you could do this by hand, but it is very tedious, it's very long, and why would you want to do that when you can do it in Matlab using an iterative method? There are different ways you can go about doing this. However, for Euler's method, I find that a count-controlled loop, so the very bottom iterative method in this list, it makes the most sense to use. And I'll show you that in a minute. But before we do that, I do want to make a couple special mentions of Matlab tips. Because I do understand that this is usually where students tend to struggle the most in this course, is just how do we get Matlab to do what we want. And so the first thing is you need to know what your objective is. So what do you want to accomplish when you're writing a Matlab script? That's very important, because if you don't know your objective, it is a little bit difficult to try and tell Matlab what you want it to do. The second most important thing, and this in particular is, I think, where people run into the most trouble, is that you need to know the syntax. So basically, you need to know how to tell Matlab what to do in a way that Matlab will understand it. Matlab isn't a mind reader, so you need to know how to write a script that Matlab recognizes and can read and then do what you want it to do. So in order to do that, you need to take it just one line at a time. Matlab will read each line of your script as it's written in the order that you have input it in. So whatever you want it to read first, make sure you put it first in your script lines. And that's especially important when you're defining variables. The next thing that I find personally helpful is to include notes in your code, and I'll show you how to do that as well, in order to make it easy to follow and see what the train of thought is, so that you personally know, and whoever is running your script, or when you're taking this course, your grader, your TA, or the professor, it's easy for them to figure out what you're doing or what your thought process is. So let's open up Matlab and let's get started. Alright, so our problem today, or at least our first problem today, is on cancer cell growth. This is from homework 1, number 3. We're going to do part C because this is the part that requires Matlab usage. the first couple parts are all handwritten, and it's just math that you probably already know how to do, and you probably don't want to do the Euler's method by hand, because the objective of this particular video is to show you how to do it in Matlab. So we won't be doing parts A and B. We'll just be focusing on C. But we do need to read the question so that we have some background. So a certain line of cancer cells grow exponentially with a doubling time of 68 hours when they have unlimited nutrient supply. However, as the cells start to form a solid spherical tumor without a blood supply, growth at the center of the tumor becomes limited and eventually cells start to die. Exponential growth of cell number n can be expressed as shown below, where mu is the growth rate of the cells, so dn over dt equals mu times n. Then they give us the actual equation here where it's n as a function of t equals n initial time, and that's multiplied with the exponential of mu times t. So they also go on to say where n initial is the number of cancer cells at time t equals 0. And then moving on to part C here, we're going to write a Matlab program using Euler's method to compute the number n of cancer cells from t equals 0 to 480 hours using a step size of 3 hours. Assume that the cells have unlimited nutrient supply and the exponential growth model holds, and assume a single cancer cell is present at t equals 0. And then they're going to ask us to plot n versus t using the value of n obtained from the Euler's method together with the value obtained from the analytical solution. So, at least for Dr. Koh's class, typically he prefers this type of heading before you actually start writing the script. So, your name, your access ID, the date you modified the script, the homework problem, what you named the file, and personally what I like to do is I like to write the objective of the problem. So I wrote, using Euler's method to find approximate number of cancer cells at time t, comparing it to the analytical solution. And then I write some givens in the notes that they provided in the problem. So they provided the time interval, they provided the step size, and then I like to write the analytical solution equation and then the Euler's method equation. So I have it on hand, so I don't have to think about it later. But what we're going to do now is we're going to start with the approximation first. So let's make a note just to stay organized on what we're doing, and so it makes it easier to follow. If you want to make a note that Matlab is not going to read and try to use to compute something, you first type in a % sign, and notice how it changes the color of the text green. That means that Matlab is not going to read this as part of like a computation or anything. So we're going to say this is the approximation using Euler's method. So now let's define our variables. We need to know how many steps we're going to be iterating for. So basically what our maximum is going to be in terms of how many iterations we're doing. So we're going to use the variable n because that's pretty standard. So n equals 160. So you're probably wondering where I got this number from. Well, I'm going to make a note and say that this is the number of steps found by taking 480 and dividing it by 3. So why 480? Because that's our maximum of time t, and then we divided that by the step size, which is 3, and so we have 160 steps as a result. The next thing we're going to define to stay consistent with the Euler equation that I showed you in the introduction is we need to define the step size. So h equals 3, and again this is the step size, and they gave that to us in the problem. So then the next thing we need to do is we need to set our initial conditions. So in the equation, they said the number of cancer cells is defined by capital N. And they told us that the very first, so the initial N value, so the initial number of cancer cells at time t equals 0 is 1. So this is the first N value. So you're probably wondering why I wrote it this way. It will make more sense in a minute when I run the script. But all this is saying is that out of all the N values we're going to be getting when we do this approximation method, the very first one is going to be 1. And then lastly, we need to define our t initial condition for the time, and that's 0. And they told us that in the problem. So again, the reason why I am writing it like this is because we are going to be getting some other t values, or I should say based on the number that we're taking, which is defined by how many steps we're taking. And again, once I run the script, I can go on and show you, and it'll be, I think, a little bit easier to see. So now we need to actually do the iteration part of this. And for Euler's method, for loops are typically, at least I find them more intuitive to use for this type of approximation. So in order to start a for loop, type the word for. Notice how it's changed color to blue. That means we have started this for loop, and now we are going to define some things and tell it what we want it to do. So for each iteration, we need to tell it how many iterations to do. In order to do that, we're going to define I equals 1, because that's going to be the first number we're doing. And then we're going to say, we're going to go from 1 to n. So in order to give a range, use a colon. And then we're going to say n is our maximum. Notice how this is highlighted, and it's highlighted to match this n, because we're going to be taking 160 steps. So we're saying that from 1 to 160, this is how long this for loop is going to run. So we've set a limit on how many iterations we're going to do, right? So then once we've done that, you hit enter, and notice how it's indented now. So that's saying that this is all inside of the for loop. So let's input our equation for the Euler's method. In order to do that, if you recall from the slide that had Euler's method on it, it said in order to obtain the new value, you have to take the older value, or the previous value from the previous iteration, and you are going to add that to the step size times the slope. And that is how you're going to get your new value. So how that's going to look is n I plus 1, because that's saying that we're going to take whatever step we're on, and we're going to say that for the one right after, this is what we're computing. So n, and this has to be in parentheses, I plus 1, that is going to equal the old value, so that's going to be the previous value, plus your step size times your slope. So you might be wondering, well, what's our slope? So if you recall from the problem, they told us that this rate here, dn over dt, is mu times n. Well, if you recall, slope can also be expressed as a type of rate. So that's why this here, dn over dt times mu times dn over dt equals mu times n, that is our slope. So mu, I will give you what mu is because I have the value for that. Mu is going to be 0.010. So that's what mu is. And we're going to multiply that by the old n value. Want to make sure you close all your parentheses. And you can check that by clicking on it, clicking on the parenthesis, because you'll see little lines under the ones that it corresponds with. But just so that we know what this is saying, we're going to make a note. So we're going to say where 0.010 times n times ni. This is dn over dt, and again, that's a rate, but it's also representative of the slope because slopes can be expressed as rates as well. So then, that is for the number of cancer cells, but then we have to also consider the fact that we need to go through each step as well. So for each new step, for the time, we're going to say that the new time value, so ti plus 1, is going to equal I times h. So basically what this number is here, or I should say this range here, based on I, that's going to be multiplied by the step size. And you might be wondering why I'm adding some semicolons here. Basically, that's going to hide the calculations for these values. It's not going to put them in the command window down below because there's going to be quite a few of them. So it just will keep it hidden from the command window so it's not as cluttered. Otherwise, you might have some stuff going on in the command window and it might take a while. So that prevents that. Anyways, this is all the information we need for the approximation using Euler's method. So what we're going to do is you're going to hit enter. And since we're done with everything we need in this for loop, we're going to hit end, and that closes it. So basically what it's saying is that under these conditions here for this range, it's going to make these calculations. And once we hit that maximum in the range, it's going to end the loop. All right. So let's run this so that I can show you how this notation actually is working. So, yeah, sometimes you'll get this dialog box if what you're trying to do, like it just has to do with file saving pathways. But in cases like this, you just hit change folder. And if you notice over here on this side where the workspace is, you will see the things you defined, and you'll also see the things that were calculated. So let's look at these n values. So you see here where you have 1, 2, 3, 4, 5, and then it keeps going on, right? It's a lot. So remember when I said the first n, and then you have your parentheses and the 1 in the parentheses? Well, we're looking at this first one right here, so that's what that's picking up. If we were to change this to another number, so let's say 5, this is your n5. Does that make sense? So if I were to say like n10, this is your n10. So basically what it's doing is it's just a way for Matlab to recognize what n value that you're trying to pull for, or what you're trying to set, or what you're trying to read. And if you look at the maximum here, we did get up to what we wanted, right? However many steps we wanted. So that's how we know that things are fine here. I know it says here that we have 161, but that's because we define the very first one as 1. So, all right. So hopefully that makes more sense in terms of what this notation is actually looking for. And you know, just for thoroughness, this is the array for the t-values. So, and you can tell for the t-values, we want it to go to the maximum that we set, which is 480. So that all checks out, which is good. So the second part of the question, or at least in terms of what we do after we do the iteration, they want us to plot it. So if we want to plot what we calculated, we want to plot the number of cancer cells against time t. So we're going to say plot, and then you enter your x-axis variable, which is your t-value, because time is always independent, so it will always go on the x-axis. And then you're going to plot it with n, which is our number of cancer cells. So that will plot that line. And since we want to plot it with the analytical solution, we want this plot to be on the same plot. Hold on, we'll do that. So if I want to run this again, a figure will be generated. And that's what we want. So that is for the approximate solution. So let's make some space. Let's do the analytical solution next. And again, these notes are just to help us stay organized. So we do have to use slightly different variables because we don't want things to overwrite. So we're going to use m for this variable. We are going to have the same step size. So just to make a note, to make it easy to understand what we're doing, we're going to again mention that this step size or number of steps are found by taking 480 divided by 3. The step size will remain the same, and that's fine. Now we need to figure out our initial conditions, which they gave us this. And we're using m because we don't want things to overwrite. Because if you use the same variables, it will overwrite the initial ones. And we don't want that. We want two separate things. So same idea as in the approximation when we're defining things. This is the first m value. And then, again, with t1 equals 0, which we've already defined. And this is going to be the first, so this is our initial t value. So then we need to make another for loop. All right, so again, type in for. We're going to use a different variable this time, so j. Just again, we don't want things to get overwritten because that will mess things up a bit. So we're going to do the same range as we did for the approximation. So it's going to be 1 to m, so 1 to 160. And then we're going to write similarly again, but we're going to be using a different equation. So if we want to find the values for the analytical solution at different time points, we're going to use a similar notation where we're saying the new m value at each time point is going to equal, and if you recall, this is the equation we're going to be using here. So we are going to have m I times actually I am going to mention that when you look at this equation, this is a constant. This is not going to change. The only thing that will change is your time t. So this is just going to be m1. So it's just going to be 1. So we are going to have 1 times the exponential of 0.01, and we are going to multiply that by t. So each t value that we take, this iteration, then again we're going to define our t values at each step. Then we have everything we need, so we're going to end the for loop. Then we're going to plot this. So we have t against m. And since we want this and the previous plot to be on the same plot, we're going to do hold on. So let's run it. And we now have both graphs on the same figure. So now we need to actually define our axes and our title and do a legend as well so that we know what's going on, right? So in order to do that, we're going to first start with the title. So whenever you want to title a graph. So we're going to do title, open parenthesis, apostrophe, type in, let's say, cancer cell growth rate over time, apostrophe, close parenthesis. When you do the apostrophes, that is just saying that this is just text that's going to go on the title for the graph. And it's not going to be like a computational thing Matlab is going to see. It's just going to say, oh, this is just text. So we did the title. Now we need to do the x-axis. So to label an x-axis, you do x label, open parenthesis, apostrophe. And since this is the x-axis, this is going to be our time, and this is in hours. Apostrophe, close parentheses. For the y-axis, when we want to title it, we do y label, open parenthesis, apostrophe, and this is our number of cancer cells. And our number of cancer cells, apostrophe, close parentheses. And then for a legend, so we know which each line is for, we are going to go in the order that they get plotted, and that's how Matlab registers that. So we are going to do legend, open parenthesis, open brace, apostrophe, n equals approximate solution, close parenthesis, and that's going to be our first line that gets plotted, which was our approximation using Euler's method. To do the next one, we add a comma, then we do another apostrophe. We're going to say m equals analytical solution, apostrophe, close the brace, comma, and then we want to figure out where we want the legend to show up. So in order to do that, we do apostrophe, location, another apostrophe, comma, apostrophe, and we want it in, let's say, the bottom right corner. So that's going to, we have to do this in using directions. The way that Matlab does legend placement is based on like cardinal directions. So we're going to say south, east, and that's just saying that's going to be the bottom right corner, bottom right corner. Now we're going to add an apostrophe, close parenthesis, we're going to run the script, and now we have everything we want on this graph. So this is cancer cell growth rate over time. Our time is in hours on the x-axis. Number of cancer cells are on the y-axis. We have the analytical solution, which is in the red here, and our blue line represents the approximate solution using Euler's method. So that's all you need to do for this particular problem, and I hope that this sheds some light on how Matlab makes these types of computations using Euler's method.